the last lecture we talked about how to compute area moment of inertia about given axis, and then area moment of inertia about the arbitrary plane. Now we have to talk about the mass moment of inertia about the given plane and mass moment of inertia about an arbitrary plane. So how it is correlated? Mass moment of inertia. Now, if you see that x, this is your y, and this is your z axis, and this is your complete mass having m as the total mass and also density given as, then you have volume which is given as that your m which is given by rho into v constant. Either you can find the mass moment of inertia directly or volume moment of inertia. So fine, so let us say when m is the mass, so this can be written as rho into dv as a volume. If you want to find out, let's say I of x in this case, mass moment of inertia ij. So what of this particular point is given by x, right? That it's showing that this particular distance is your r, which is that axis that here so if you try to just write this particular thing, y this is your y and above this x this is your x, so you will see that this y square, right? Now if you have, it means that point over here is perpendicular to this r and z. Let's say this z is really varying. This is your z, but the distance of this particular mass with respect to z is given by position vector r, right? So this position vector r, which is perpendicular to nothing but x square plus y square. Now if you want to define your ij, then it is defined as moment of inertia is defined as r square, and it is integrated over whole mass. You can also define it as rho times r square dv. So it means that this can be correlated with your this is your mass moment of inertia, mass moment of inertia. This is your volume moment of inertia. And now let's say that it is a thin plate. So for right of thickness d. So this can be written as P times PA, right? In that case, R square dA called inertia. That mass moment of inertia, which is given by this, can also be expressed in terms of volume moment of inertia. It can also be expressed in terms of if this if here rho is constant. If rho is constant. So what will be your, since R is nothing but x square plus y square, so you will be getting quantity. Similarly, if you have to find out your Ix, then what will you do? Y square plus z square, and your Iy will be given by x, and Iy will be given by x square plus z square into. Okay? And this is how you define the moment of inertia for the mass moment of inertia, or in space x, y, z is how you try to define. Now the next question that has to be asked is, what will, and sorry, so here also exists product of inertia. Product of inertia here, but on, you know, different planes. So if you have to find out Ixy, you will see that the, if you take y, so it means that on xy this will be just y into the mass product of inertia. Yes, similarly yz, we will have yz dm mass, and then zs, which is also define product of inertia in the space. However, product of inertia has to be defined over a given plane. So that's, since there are x, y, z planes, so there. Now the second question is that, as far as we know our axis like this. Now if we have to find out moment of inertia arbitrary plane, then how? So let's say this is your x-axis. Now the second question that is being asked is mass moment of inertia about arbitrary, which is given by the direction lambda. So let's say you are having your mass m, your x-axis is this, y-axis is this, and z-axis is this. So, and this is your O, right? If you have to find out the product of inertia about some direction, let's say arbitrary axis, which is given by, represented by the direction lambda cap, right? And let's say the position vector of this particular event is this is your lambda. If it is going to make theta with this particular direction, then how to find out the moment of inertia with this given? Given at ix iy ixy iyx ix iy iz ixy yz and zx. So these quantities are given, right? And what is given is the direction of your lambda. So if we assume that this particular axis is making one direction, then how you are going to how you are going to mass moment of inertia would be that what we will do, we will draw a perpendicular line. Now what will be the P? R is the magnitude of your R, perpendicular to this one, then your I lambda is defined as square from the fundamental principle. What is your P? If R is magnitude of R, you will see that this lambda magnitude is obviously, and their magnitude of R, which is given like this, and sine theta r sine theta has nothing but lambda cross r, right? So this particular thing, lambda cross r magnitude. So this particular thing is nothing but to write this I lambda in terms of your lambda which is given and positioned at r, you can say that I of lambda is given by square, which is nothing but cross p lambda cross r lambda cross r whole square, and here into, okay. So what is lambda? Sorry, what is lambda? Lambda is nothing. Let's assume that lambda x, lambda y along y, lambda z along k, and what is your r? R is the position vector, so it's given by component. What will be your lambda cross r? Lambda cross r will be I x y and x, and times lambda y minus y times lambda z plus x plus y times lambda x minus x. Okay, so this particular quantity is given with this, and the mod of this one is equals to mod of this whole square. Okay, so this way you can write I lambda is equals to lambda mod of lambda cross r is nothing but this z lambda y minus y lambda z whole square m plus x lambda z minus z whole square dm your y lambda x minus x lambda z whole square into dm. And what you will basically get square lambda y square plus y square lambda z square and y lambda z, right, plus x square lambda z square plus z square lambda y square x z lambda x lambda z, and finally y square lambda x square plus x square lambda z x y x lambda z. Now let's take out these are the constant terms lambda x lambda y lambda. First of all, let us collect the terms lambda x square. So what you will be getting here is square plus z square again. And collect y lambda y square. So you will be getting this one, and where is on the y? Y z y and z and y z and y z x y sorry x y and x z minus lambda x, that's fine, and this one is y lambda x minus x lambda y x lambda y x lambda y, okay. And so it means that when you do this y, okay, so you are getting this and this, so when z square plus x square plus then z, and the z square is nothing but m, right? Afterwards, what you are going to get, let's collect the terms of y at z, so minus lambda y lambda z, this to x xz, yeah? And finally you have this one which is given by minus 2 x, oh sorry, lambda x lambda y by finally, but your I x I x, this is your I y, this is your I z, this is your I x y, this is your I x z, and this is your I y. So finally, you will see that this I lambda is written in terms of ix, iy, iz, ixy, iy, z, yz. So it means that yz, right? Yz. Okay. So finally, your I lambda is given lambda x square ix plus lambda y square iy plus lambda z square iz minus 2 times lambda x lambda y xy minus y lambda yz minus x, and this is what is your for arbitrary formula for arbitrary value mass moment of inertia about any this is the formula for mass moment of inertia about any arbitrary plane or the axis which is passing through the point, and it is in space. Okay, and you will also notice that if you try to find out the locus of this particular plane. For example, geometrically we saw on one plane, xy plane or yz plane, we saw turned out to be Mohr circle, which we call as Mohr circle. But in this case, draw about the principal axis ix, iy, iz. In that case, you will see that the equation of curve will be. So with this, we end this.